To find the expected value of a continuous random variable with PDF f, we can evaluate the integral over the sample space of x f of x. If we're given the CDF, we can find f by differentiation. However, we need to be careful at the boundary points. Suppose our PDF has an atom corresponding to the probability that x equals a specific value not being 0. Then at x equals a, our CDF will abruptly increase. This is called a jump discontinuity. We can identify when a jump discontinuity exists by finding the value of the CDF as we get close to a boundary, then finding the value of the CDF at the boundary. If the two are equal, there is no jump discontinuity, but otherwise their difference is the probability of the boundary value. So let x have CDF. Let's find the expected value of x. Note that the boundary points are at x equals 0, 1, and 4. So we should use the limit formulation, but informally, if x is slightly less than 0, f of x is 0. If x actually is 0, then f of x is 0. And if x is slightly more than 0, f of x is about equal to 0. Since all three values are up to approximate equality in agreement, f is continuous at x equals 0. Likewise, if x is slightly less than 1, f of x is about a quarter. If x is 1, f of x is actually a quarter. And if x is slightly more, f of x is approximately a quarter. And again, all three values agree up to approximate equality, so f is continuous at x equals 1, and similarly around x equals 4. Now this means that f is continuous, and so the continuity of the cumulative distribution function means that there are no atoms, so the probability of x equaling any specific value is going to be 0 for any value of a. This means we can differentiate to find the PDF and ignore the boundaries. So the PDF will be, so we can find the expected value. Since the PDF is 0 everywhere outside the interval from 0 to 4, we only need to worry about the interval between 0 and 4. And since our rule changes at x equals 1, we'll have an integral from 0 to 1 using that first function, plus the integral from 1 to 4 using the second function. And so we find Now, what happens if we have an atomic probability where the probability of a specific value is not 0? We could write something like this where the integral about a single point is some value, but if I wrote that, they'd revoke my mathematician card, so I'll say that strictly speaking, we need to limit around this point. So, for example, this probability that x is less than or equal to b is going to be that limit plus the probability. But we'll simplify our notation and just drop the limit part of it, where it's understood that our integral doesn't actually include that boundary. So, for example, we might have a CDF like this. So note the boundary points are at x equals 0, 1, and 2. And we could go through that analysis again. If x is slightly less than 0, f of x is 0. If x is 0, f of x is 0. And if x is slightly more, f of x is close to 0. Since all three values are up to approximate equality, f is continuous. However, if x is slightly less than 1, f of x is about a quarter. But at x equals 1, f of x equals 1/2. So f is not continuous at x equals 1. And if x is slightly less than 2, f of x is about 1, while if x is 2 or more, f of x is 1, so f is continuous at x equals 2. And so this discontinuity at x equals 1 will require some special handling. We'll indicate that on our PDF with a star, but we can find the PDF for any other value by differentiating the CDF. So differentiating gives us our PDF everywhere except at x equals 1. Now we have an atomic probability at x equals 1. This means the probability that x is equal to 1 isn't 0. To find what this probability is, we note that for x slightly less than 1, the probability that x is less than or equal to slightly less than 1 is going to be 1/4. But the probability that x is less than or equal to actually 1 is 1/2. And so that difference, 1/2, must be the probability that x equals 1. So to find our expectation, again, the PDF is 0 everywhere outside of the interval from 0 to 2, so we only need to evaluate the integral from 0 to 2. Our rule splits at 1, and there's an atomic probability that x is equal to 1. And so our expected value will be, and we find